In the popular imagination, the internet emerged overnight in the mid-1990s with the creation of the commercial browser and services employing that browser. In fact, the internet developed for more than 2 decades prior to the emergence of the browser, starting from the first government funding at the Defense Advanced Research Project Agency, DARPA, in the late 1960s and the National Science Foundation, NSF, in the 1980s. Hence, there is no question that the infrastructure came first. The internet infrastructure of the mid-1990s employed many components and inventions inherited from the government-funded efforts. Both the commercial internet and its government-sponsored predecessor are packet switching networks. While the internet is certainly not the first packet switching network to be deployed, the commercial internet has obtained a size that makes it the largest ever built. In a packet switching network, a computer at one end packages information into a series of discrete messages. Each message is of a finite size. As part of initial processing by the packet switching system, larger messages were divided into smaller packets. All of the participating computers use the same conventions for messages and packets. Messages successfully traveled between computers when the sending and receiving computer standardized on the same procedures for breaking up and reassembling packets. Sending data between two such locations relies on something called protocols, standardized software commands that organize the procedures for moving data between routers, computers, and the various physical layers of the network. Protocols also define rules for how data are formatted as they travel over the network. In 1982, one design became the standard for the network organized by DARPA, a protocol known as TCP/IP, which stands for Transmission Control Protocol, Internet Protocol. A study shows that researchers wrote the first version, replacing an outmoded protocol that previously had run the DARPA network. Over time, the technical community found incremental ways to change the protocol to accommodate large-scale deployment of infrastructure and applications. TCP/IP had the same role in the government-sponsored and commercial internet. It defined the headers, or labels, at the beginning and end of a packet. Those headers informed a computer processor how to reassemble the packets, reproducing what had been sent. By the mid-1980s, all Unix-based computing systems built that interface into their operating systems, and in the 1990s, virtually every computing system could accommodate it. An example of TCP/IP in action may help to illustrate its role. Consider sending messages from one computer, say at Columbia University in New York, to another, say at Stanford University in California. In the 1980s, such an action involved the following steps. A user of a workstation, typically using a computer costing tens of thousands of dollars, would compose the message and then issue a command to send it. This command would cause the data to be broken into TCP/IP packets, going to a central mail machine at Columbia, and then a destination mail machine at Stanford. In between the central mail machine and destination mail machine, the file would be broken down into pieces and completely reassembled at the final destination. During that transmission from one machine to another, the file typically traveled through one or more routers, connecting various networks and telephone lines. At the outbound site, it was typically convenient to send through a central mail server, though that did not need to be true at the inbound site. At the Stanford server, the local computer would translate the data into a message readable on another person's workstation. If something went wrong, say a typographical error in the address, then another set of processes would be initiated, which would send another message back to the original author that something had failed along the way. These technical characteristics define one of the striking economic traits of internet infrastructure. It requires considerable coordination. First, designers of hardware and software must design equipment to work with other equipment, and upgrades must meet a similar requirement. Second, efficient daily operations of the internet require a wide array of equipment to seamlessly operate with one another. Indeed, the widespread adoption of TCP/IP partly explains how so many participants coordinate their activity, as the protocol acts as a focal point around which many participants organize their activities at very low transaction costs. Another key factor, especially during this early period, helped coordinate activity: a principle called end-to-end. This principle emerged in the early 1980s to describe a network where the switches and routers retained general functionality, moving data between computers, but did not perform any processing. This was summarized in the phrase, "The intelligence resided at the edges of the network." Any application could work with any other at any edge, so long as the routers moved the data between locations. End-to-end had substantial economic consequences for the deployment of the commercial internet. At the time of its invention, it was a radical engineering concept. It differed from the principles governing the telephone network, where the switching equipment performed the essential processing activities. In traditional telephony, the end of the network, the telephone handset, contained little functionality. For a number of reasons, this departure from precedent was supported by many outsiders to the established industry, especially researchers in computing. Hence, the internet encountered a mix of benign indifference and active resistance from many established firms in the communications market, especially in the telephone industry, and many did not invest in the technology, which later led many to be unprepared as suppliers to the commercial internet in the mid-1990s. End-to-end also had large economic consequences for users. First, the internet largely employed existing capital at many installations with comparatively minor software retrofits, repurposing capital for any new function as long as it remained consistent with end-to-end. Repurposing of existing capital had pragmatic economic advantages, such as lowering adoption costs. It also permitted internet applications and infrastructure to benefit from the same technical changes shaping other parts of computing. Accommodating heterogeneous installations supported another, and in the long run, especially important economic benefit. It permitted users with distinct conditions to participate on the same communications network and use its applications, such as email.